เราเริ่มตั้งคำถามเกี่ยวกับกลไกการทำงานพื้นฐานของธรรมชาติมาตั้งแต่ครั้งโบราณกาลองค์ความรู้ที่ได้ถูกส่งต่อจากรุ่นสู่รุ่นถูกพัฒนาปรับเปลี่ยนต่อยอดผ่านการค้นคว้าทดลองตั้งสมมติฐานและพิสูจน์ทางทฤษฎีเพื่อให้เข้าใจถูกต้องมากขึ้นฟิสิกส์ทฤษฎีถือเป็นวิทยาศาสตร์พื้นฐานที่สำคัญอันหนึ่งที่อาศัยแบบจำลองทางคณิตศาสตร์ในการไขความลับความเป็นไปของสิ่งที่อยู่รอบตัวเราตั้งแต่ระดับอะตอมไปจนถึงระดับจักรวาลส่วนหนึ่งของผลสำฤทธิ์ที่มนุษย์ทำความเข้าใจธรรมชาติผ่านภาษาทางคณิตศาสตร์คือเทคโนโลยีอันหลากหลายที่อำนวยความสะดวกในชีวิตประจำวันไม่ว่าจะเป็นโทรศัพท์มือถือคอมพิวเตอร์หรือแม้แต่โครงข่ายอินเทอร์เน็ตที่ทำให้โลกอันกว้างใหญ่แคบลงไปเพียงปลายนิ้วสัมผัสยังมีคำถามอีกมากมายที่เรายังตอบไม่ได้ทั้งหมดเกี่ยวกับธรรมชาติซึ่งถือว่าเป็นเรื่องที่ท้าทายและรอคอยให้นักวิทยาศาสตร์เข้าไปค้นหาคำตอบในอนาคตในปัจจุบันบุคลากรของวิทยาลัยเพื่อการค้นคว้าระดับรากฐานถือได้ว่าเป็นส่วนหนึ่งในการค้นหาคำตอบของคำถามข้างต้นผ่านการทำงานวิจัยหลากหลายที่ให้หัวข้อที่ล้ำหน้า
Okay, good afternoon, everyone, and welcome to IF Colloquium online seminar number 5, organized by the Institute for Fundamental Study, Naleson University, Thailand. My name is Circulate Yukong. I am IF Deputy Director of Strategy, and it is a pleasure to welcome everyone to this afternoon online event. Let me first give you the idea why do we need to do this kind of activity. Most of the time, academic conversation would normally circulate among the scientists, just bridging the gap between the science world and general audiences is very crucial for the country in this current competitive world. Then the Institute for Fundamental Study would like to provide a platform for people who are interested in physics, mathematics, and other related fields. Come and enjoy in progress of advanced research. For this talk number 5, we are very pleased to have Dr. Supachai Ponglastakun from Simpakon University to give us a talk on the topic physics of compact objects, some aspects. Let me spend a bit more time to introduce our speaker formally. Dr. Supachai Ponglastakun completed his bachelor degree in physics from Mahidol University. Then he went further for his master degree in physics at Chulalongkorn University and then PhD in applied mathematics at University of Sheffield, United Kingdom. At the moment, he is working as a lecturer at Department of Physics, Faculty of Science, Simpakon University, Thailand. His research interest is on various aspects of general relativity, especially black hole. Well, correct me if I'm wrong. The talk will be roughly 40 minutes long. Before I stop during the talk, if you have questions, you could put them in the comments. Our staff will collect all the questions and deliver to the speaker at the end. Anyway, without further ado, let me give this screen to our speaker, Dr. Supachai Ponglastakun.
Okay. Can you hear me?
Yes.
All right. Just a little bit. Okay. So can I start now?
Yeah, sure. Of course.
Okay. Hi everyone. First of all, I'd like to say thank you to Ajahn Sikharin and Joe for giving me this opportunity to talk about my research. Today, I'm going to talk about the physics of compact objects. And here's the plan of my talk. So I'll start by introduce a concept of compact objects. What are they and why are they interesting? Then I'll discuss about my research projects, which are black holes, quasi-normal modes, and holographic neutron stars. So I'll start by telling you guys a little bit about compact object. Well, as the name suggests, a compact object is a very high density object with a very high mass, but relatively small in radius. And in particular, there are stellar remnants, thus white dwarfs, neutron star, black holes, all sort of things. They are all complex objects in my interpretation. And also these include a so-called exotic stars. And by exotic, I refer to a hypothetical objects where their internal structures are made of other materials rather than electron, neutron, and protons. For example, in this sector, you could also have something like a quark star, boson star, for example, and Grover stars, and also a fuzzball in string theory as well. So the next question is why should we pay attention to these objects? So basically, that's because the physics involved with these objects, they are in the strong gravity regimes. And that means these objects are a good place to test our idea about general relativity. And moreover, because we know that nowadays the strong physics, the strong gravity physics has become more accessible because we are in the era of the gravitational wave and black hole shadows. I'll spend some more slides further to explain about to you what are they. I mean the gravitational wave and the shadows. Right. So basically, the black hole shadows refers to an image of the black holes. And since black holes in nature, they are usually surrounded by a bright, hot material called accretion disk. But the black hole itself absorbs every electromagnetic radiation. Thus, an image of the black holes is actually, in this figures, is actually a black dark block at the center of an image, and that's the location of the black holes. And at the edge of the black hole image, you will see there's some tiny ring of light or photon rings, which is an orbit of the photon that will gradually falling down into the black holes. So what can we learn from the black hole shadows? First of all, since we know that the size and the shape of the shadow are determined by the GR equation, therefore we can use the appearance of the shadow to test our idea about general relativity. We can tell by looking at the size and the shape of the shadow whether they are described by GR or any other alternative theories. Moreover, physicists believe that if a black hole has an extra structure, hair structure, the hair structure could alter size and shape of the black hole shadows as well, and this could validate or invalidate the so-called no-hair theorem in GR. And from our observation of the black holes M87, it is from the results that we have, it suggests that at the moment GR is a preferred theory. So we still don't see any deviation from GR by observing M87 shadows. And moreover, researchers use the black hole image to put more constraint on modified gravity theories, and they found that by just using an image of the black holes, they can put more constraint on the modified gravity theory better than the test that they have done before by using the test from the solar system. And they can improve it by a factor of 500. So with the presence of the black hole image, now physicists, we have a new tool to study about theory of gravity and use them to constrain many other theories that might be the candidate of the gravitational theories. And also, since black hole shadows give us a very close look of the black holes, therefore it is possible to use a shadow to learn about a complex structures that surround black holes, such as an accretion disk, jets, and also a photon ring. And actually, very recently, a team of the at the Event Horizon Telescope, they can observe a polarization of light that emit from a photon ring around the black holes, and they can infer that by just looking at the pattern of the polarization of light that coming out from the photon rings, that around the black holes, around the M87 black holes, there must be a very strong magnetic field around the black holes. And this is a very crucial result. That's because we physicists, we expect that, around the black holes where the valence phenomena occurs, like you have a very hot gas and you also have a very high energy of jets, for example. They are all created by we believe that they are all created, all the mechanisms of those phenomena has to involve with the strong magnetic fields. And this is the first evidence that we know that there must be a very strong magnetic field around the supermassive black holes. That's one example. And that's for the shadows. And then I'll move further to the gravitational wave. Well, as you guys know, according to GR, when a mass moving through space-time, or you have a mass that oscillates in a non-spherical way, it creates a ripple of space-time which carry energy away from the source. And this radiation, this ripple of space-time is the gravitational waves. And the source of that emits the gravitational wave is usually a binary system of compact objects. Especially nowadays, we focus on neutron stars and black holes to observe the gravitational wave. And down here is a diagram of explaining what happened to gravitational wave at each phase of the binary system. So you can see that the amplitude of the gravitational wave increases as the star moving towards each other. And the amplitude of the gravitational wave reached its maximum when the star merged to each other. And after the merging, you end up with the final products, and the gravitational wave will enter the phase called the ring down phase, where the amplitude is decay with time. And the ring down phase here is dominantly described by a so-called cosine normal mode. And I will come back to this later when I'm going to talk about my research. So you could ask the same thing, that what can we learn by looking at the gravitational wave? The most straightforward thing is we will know roughly how many stellar mass black holes are out there, because normally the number of the gravitational wave events roughly indicate the number of the population of these black holes in the universe. And moreover, for a more fundamental side, lots of physics parameters are encoded within the pattern of the gravitational wave. We know that different sources emit a different pattern of the gravitational waves. In addition, by measuring the pattern of the ring down phase that I just explained to you guys before, we can deduce the black hole mass and also the spin, which are these two are important black hole parameters that we want to know. And also we can also use the pattern of the gravitational wave to study about what happened inside the star, because we expect that a different equation of state that explain physics that happens inside a neutron star will produce a characteristic pattern of gravitational wave. So if you have a different equation of state, or you change your model that explain things that happened inside the star, you expect to have a different pattern of gravitational wave. And another cool things about gravitational wave is recently physicists just used the knowledge of the merging event to confirm the Hawking's area law theorems. That's the theorems about the that's the theorem that's about the area of the black holes, and it is just confirmed by looking at the gravitational wave data. And also very recently, because we expect that different compact object will give you a different or distinguishable pattern of gravitational wave. So we expect that different compact so a team of physicists, they calculate the pattern of the gravitational wave of a fuzzball. Fuzzball is an object in string theory where it is believed that you could replace a black hole in standard GR with a fuzzball. And they found that the gravitational wave property from the fuzzball is significantly different from those in GR. So this is another way that we can use this gravitational wave to prove a new physics, if you like. So now I want to talk about a cosine normal mode, which I described before, and as I mentioned, it mainly describes the ring down phase of the gravitational wave. So the idea of the cosine normal mode is quite simple. When we perturb a black hole will vibrate in response to our perturbation, and the oscillation mode that's describing these vibrations, they are quasi normal mode. And the word quasi is used here to distinguish them from a normal mode that we are familiar in the physics course. And the cosine normal modes are normally associated with a complex frequency, which can be written in this form. Sorry. So you can write it down as a real and imaginary part like this. So it's a complex frequency. And if you are in this business like myself, you probably know that the cosine mode also provides us a way to test a classical stability of a black hole solution. So that's my interest in the cosine mode business. Right. And okay, so this is what I really like to discuss. This is one of my projects that I've done with my ex-boss in Korea. In this project, I calculate the cosine normal modes of a higher dimensional rotating black holes in asymptotically the sister space. So the matrix that I use is the Meyer-Perry black holes, which is rotating black holes in D dimension. However, I simplified the problem further by considering just a black hole that has only one rotation axis, because in high dimension, the black holes can rotate they have many rotational axes. But in this work, we focus on a simpler case where just one rotation axis. So we have one spin parameter, which is denoted by the parameter A here. I'm not sure if you can see the cursor, but if you look at the matrix here, the parameter A will describe the spin of the black holes. And as usual, lambda here is the cosmological constant, and m is the black hole mass. And also the sphere, the d minus 4-dimensional sphere, is described by this relation. Okay, so with the sister setup, that means we should lambda to be positive. Black holes had at least three horizons. So you have a Cauchy horizon, event horizon, and also cosmological horizon. So just to give you an overview about the solution itself. So we plot the black hole phase space like this. So here's the phase space of the black holes, where the y-axis is the lambda and the x-axis is the spin parameter. So in these figures, I show you phase space of black holes in 4, 5, 6, and 7 dimensions. And the gray area denotes denotes the area where the black hole solution exists with 3 horizons. And we found something interesting here, because it turns out that when the space-time dimension is just 4 and 5, there seems to be a cutoff on a spin parameters. By a cutoff, I mean you cannot go any higher in A in 4 and 5 dimensions here, because you can see that there is no black hole solution after some certain value of A. However, this upper bound does not exist anymore when you go higher than 5 dimensions. So from our exploration, we found that for 6 and 7 dimension, for example, we can extend the phase space to the right hand. That means you could go up in the value of A to a higher values. That's interesting. And since we are interested in the scalar perturbation, so the equation that describes the scalar perturbation on the Mayer-Perry black holes is just a Colloquium equation that takes this form, and the answers for the scalar fields can be written down as in the separation form like this. So basically, you put this equation back into the Colloquium equation with the background of the Mayer-Perry black holes, and you'll be able to separate the perturbation equation into 2 parts. The first part I call it as radial part, because it contains all the function that depends on the radial coordinate r. And another equation is the angular equations, where all the theta terms will appear in this equation. The common factors that they have in both parts of the perturbation equation is they contain the so-called separation constant here. So basically, we want to calculate the quasi normal frequency of the omega, which are complex numbers, and that's determined by this omega here. So basically, we're gonna solve these 2 equations and looking for an omega. However, since the value of the A here is also determined by the equation itself, then that means you have to solve these 2 equations at the same time and looking for the omega and the big A here for that satisfy all the requirements. So in order to solve these equations, so we need to specify some boundary conditions, and the boundary condition that give a quasi normal frequency will be like this. So at the black hole horizons, all the wave moving in, nothing comes out. And on the other hand, on the far side of the space-time at the cosmological horizons, we allow only just an outgoing wave, nothing comes in again. So we allow wave to dissipate through black hole horizons and cosmological horizons. However, if we consider in a so-called slow rotating limit, so that means we consider in the case that the spin parameter A is very, very small compared to the mass of the black holes, the separation constant here, the big A here, can be expressed explicitly. And also in the near extremal limit, where 2 horizons are merging together, the quasi normal frequency can be written down in closed form like this. So you can see that the formula can be expressed analytically. And as I promised to you, so you can see that there is real part here and also an imaginary part here. So on the imaginary part, there is an n parameter. The n parameter acts like a energy level, because the omega, the frequency will be discrete, and n can take the value of 0, 1, 2, and 3. So n equal to 0 will be the most fundamental mode, right? And the potentials V0 are expressed in this group of constant. Okay, so the next is this is the result that we use that formula on the previous slide to plot, and is this the plots of the quasi-normal frequencies in the near extremal limit against the number of the dimensions. So from a quick look, we can see that as we go into higher and higher dimensions, the black holes in higher and higher dimensions, they become more stable because the imaginary part of the omega become more and more negative. So then you have an exponentially decay mode, stronger and stronger as number of dimension increases. However, when you want to go beyond the near extremal and the slowly rotating limit, then analytical calculation is not possible. Then you need to solve the equation, the radial and the angular equation numerically, and like I said before, you have to find an omega and the big A and the separation constant that satisfy the boundary condition of the cosine mode at the same time. So here I plot the omegas against the spin parameters of the black holes. Here is the black holes in 5 dimensions, for example, and we still see that in 5 dimension black holes they are linearly stable, and we found the same features. We found the same phenomena when we increase the number of dimensions as well. We try to study black holes in 6, 7, 8, 9 dimension, and they are all stable. So to summarize the first project, the key message that we learned from this is we now know that black holes in the rotating black holes, Mayer-Perry black holes in the system, they are stable against the scalar perturbation. We found not a single unstable mode at all. However, another interesting thing is we found that there is no evidence of superradiance in the sister sector. So the superradiance means that is the phenomena that you could extract rotational energy from the black holes using a scalar bosonic field. For the ADS counterpart, when you consider the Mayer-Perry black holes in anti-transistor space, there exists a superradiant mode. But in our case, in the transistor case, we found no evidence of such a mode. So yeah, this is quite amazed us at first. Right. So that's my first, well, what should I say, first half of my talk. Then I will switch the topic, and I will say something about my research, which are a holographic neutron star. This is the work that I've done in collaboration with Pinyabut Burikam and Sithichai Pin Kanchanarod at Chulalongkorn University. So before the gravitational wave era, astrophysicists start to notice that all the stellar mass black holes candidates have mass above 5 solar mass for some reason. And they have never found a candidate for a stellar mass black hole out there that has mass below this 5 solar mass before. And on the other hand, from the theoretical point of view, there should not be an upper bound on the mass as well. Black hole could be could be large, that there's no limit on the upper bound of the mass of the black holes. And also we know that the maximum mass of the neutron star should be around 2.5 or 2 solar masses, depends on the equation of state of the model that you use to describe the neutron star. So this number keeps changing, but roughly it should be around 2.5 solar masses. And when we entering into the GW era, we have this kind of diagram. So in this diagram is the diagram showing the mass of a compact object that we can observe through the gravitational wave detector. So the blue circle here denotes a black hole that has been observed by the gravitational wave collaboration, and the yellow dot down there is the neutron star. So you can see that there's some missing. There's some gap between 2.5 and 5 solar masses. That is quite weird. So what really happens, between 2 and 5 solar masses? Is there something special in this gap, or it is just somehow it is very difficult for us to detect such an object that can live in this gap? Or as a theorist, we could ask that, is there any other compact object that could fit into that mass gap? This opened a new possibility to study about exotic star, like I mentioned before, like quark star, strange star, and so on and so on. However, very recently, an anticlimax occurred when we have more data from the LIGO Virgo coming in. It turns out that there are 2 events that the final products of the merging have mass who live within this mass gap. In particular, they are neutron star merging, and as the final products, they produce some compact object that has mass around 2.7 to 2.8 solar masses, and another event produce the final products that has mass around 3 to 4 solar masses. The nature of these objects is not clear as far as I know, but we kind of convinced that there must be a black hole with mass below 5 solar masses. So if that's true, then some remaining question is, can black holes below 5 solar masses born directly from gravitational collapse? Because these objects they are black holes that has mass below 5, but they're born with a merging event. And also, of course, we can ask that, is there any exotic object out there in the universe? And another interesting question is, how can we use the gravitational wave and the merging event to study about what really happens inside a neutron star? Can some model of neutron star, because equation of state of neutron star is not it still remains as an open question in research. So then is it possible that we somehow use some equation of state that can use a much more massive neutron star than we have before? And actually, there's a study by Neller where they analyze an equation of state of neutron star, and their results suggest that it is possible that the neutron star, at the core of the neutron star, there could be a quark nuclear matter inside. So this means that a core of the neutron star can be purely consist of quarks, and this leads us to a question that could neutron star exist with a multi-quark core, and if yes, if it can, how can we use, or how can we distinguish the neutron star with a multi-quark core from other neutron star model that they are out there in the literature. That's our research question basically. So so for this reason, we're going to study the neutron star that has a multi-quark at the core. And in this case, we use the holographic model called the Sakai-Tsukimoto model to explain the physics of quark inside the neutron stars. And that means the equation of state of the quark nuclear matter will be derived and explored by using the SS model here. And in fact, the equation of state and thermodynamic properties of the multi-quark nuclear matters, they are already studied back in 2010 by Piyambut, Ekapong, and Sithichai already. And recently, Sithichai and Piyambut also, used the equation of state of the quark nuclear matter and construct a massive neutron star with the holographic multi-quark core. And they found that the neutron star could have a mass range from 1.96 to 2.23 solar masses with a radii about 14 and 11 kilometers. So now we know that the neutron star with the holographic nuclear matters, holographic multi-quark core exists. I mean, well, theoretically. The next thing that we want is we want to not observe. We want to find some signatures of this type of the neutron star. So that leads us to another calculation where we consider a so-called tidal deformability. So normally when you try to study a neutron star or compact object, you would normally describe the star by their mass, the star radius, or its compactness. Compactness defined as a mass over radius of a star. So there is another parameter, observable parameter, that is called tidal deformability, and usually this parameter will be denoted by the factor lambda. So lambda here is not the cosmological constant anymore, is the tidal deformability. And in brief, the tidal deformability measures how a star deforms under tidal fields that created by a star companion. So if you take a look at the left figures here, it shows the tidal effects. You can see that when a star deforms, the shape, its shape change as they move towards each other. It also affects the gravitational wave that they emit too. On the right hand side, this is the figures that I got from this paper that is done by Chassi Onu 2020. And in these figures, they plot the amplitude of the gravitational waves before the merging event, and they plot it in three different ways by varying the tidal deformability. So they found that the larger the lambda, the more gravitational wave phase will shift toward the left-hand side. And from this knowledge, we can use this kind of signature to use the gravitational wave to measure the tidal deformability of a star. So that leads us to the next project, where we calculate the tidal deformability and also the radial pulsation of the holographic neutron stars. Well, the result from this project is that we found that the lambdas or the tidal deformability, they are still within a physically viable range under the present observation. And also, we also found that for the stable fundamental mode frequency, this frequency explain is the frequency of how star oscillated under the perturbation, and and we found that the frequency is at about 5 to 6 kilohertz. And after we're done with this work, we move a little bit further by adding the rotating effects into the pictures. So in this work, we calculate the following quantity that relate to the rotations. We calculate the star moment of inertia. We calculate the so-called tidal love number. Tidal love number is the deformability that happens when you have a spinning object. And also the quadrupole moment of a, slowly rotating neutron stars. And by slowly rotating neutron star, I mean the background matrix that I will use will look like this. So, okay, so the matrix here, you can treat this matrix as it is explained an isolated non-rotating background with some correction terms that will represent the rotation and the deformation of a star. And now we can treat these correction terms as a perturbation on a spherical object. So that's how we looked at this metric. And in the matrix here, you can see that there's a big function. There's a function h, s, and k. These three functions represent or describe how the metric deform away from a spherical symmetry. P2 here is just a Legendre polynomial. And the spin parameters will be denoted by the function omega here. And of course, mass, the accumulated mass of the star will be related to the metric component in the usual way that we are familiar. And we will assume that the nuclear matter inside of the star takes a perfect fluid form, where the density, the rho, and the pressure profiles will be created from the Sakai-Sugimoto models. This is where the holographic things coming into the project. And with the perfect fluid and the Einstein field equation, we can solve the Einstein field equation, and at the zero order, we obtain the Tolman-Oppenheimer-Volkow equation, which is three first order differential equation like this. So basically, with the profile of the density and the pressure, we can solve this equation, and we can plot a diagram that looks like this. So this is a diagram of the mass versus radius diagram, right? In this plot, each point refers to a star profile with a specific mass and radius, where a star profile, one star profile depends on one specific value of central density. So in the case where all the stars are pure multi-quarks, which is represented by this curve, you can see that the maximum mass is around 2.2 or 2.3 solar masses, and the maximum radius is about 13.2. However, in the case of the mixed material where you have a multi-quark core at the center and at the outer core you have some outer nuclear matters, the star can be much larger in size, because we can see that the radius go further into the right hand side. This is just the first. This is just a zero order of the Einstein field equation. And to calculate or to induce the spin effects, we have to include the perturbation. And at first order, only one component of the Einstein field equation remains non-zero, and it gives us this differential equation that describes how the star spin or rotated. And basically, all we need to do is we solve this differential equation and try to obtain the omega-1 profile. Once we obtain the omega-1 profile, we can use this formula to calculate the moment of inertia of the neutron stars. So basically, you need to put rho and p profile from your holographic model, and you have to also fit in the star profile that you obtain from your zero order calculation into this equation, and then you solve for the omegas. And once you got the omega 1, you can determine the star moment of inertia by these formulas. And here is some example of the moment of inertia plot against a star compactness. So you can see that for a pure quark star, it has much higher moment of inertia at a small compactness. However, when we go to high compactness, all the different type of the star that we consider here, their moment of inertia converge to some values. They're not exactly the same value, but the way that we show in this scale makes it looks like that, but it's a very, very close number. And finally, we also try to calculate the quadrupole moment and the rotational love numbers as well. And that is, of course, coming from the deformation part of the matrix, which is the second order. And that means you have to solve these equations at the same time. And the difficulty is you have to have the information. You have to have a star profile that you got from a zero order, and you must have an profile from the omega 1 that you get from the first order calculation, and put everything into these equations and then solve it numerically. And the quadrupole moment can be obtained by matching the boundary condition of this equation, matching boundary condition between at the edge of the star and the outside of a star. And the rotational love numbers are calculated from this relation. The result is very similar to the I. So this is Q and lambda plus against C. So you can see that the trend is very much similar to the moment of inertia. And lastly, we also found some universality in the relation between I, love, and Q numbers. In all the cases that we have considered here, they are all become indistinguishable when we plot in this, when we express this in this fashion. And in fact, this behavior is expected because from the previous study of Yuki and his team, they study a rotating neutron star as well, but they use a different equation of state, and they also found the similar universality like this. So this is kind of the expected results, and it's very interesting to understand what really happens, why we have this universality. That is something that we have to figure it out. Okay, so that's the last thing that I like to say. Let me summarize a few things. First, we found that the neutron star with a holographic multi-quark core could be possible. And from our recent study, we calculate the moment of inertia and tidal deformabilities, and also the quadrupole moment of a neutron star. And we hope that this calculation could help us to pinpoint or to validate the equation of state of the neutron star by using some observation from gravitational waves or the others. And one last thing that I'd like to comment is, at the moment, we try to study how the gravitational wave that emit from this type of neutron star looks like. So we hope that this gravitational wave result could help us again to pinpoint, to validate or invalidate our model from the observation. And that's everything that I want to say. Thank you.
Okay. All right. Okay. Thank you very much for this very wonderful talk, I would say. I learned a lot from you today about this kind of fancy compact objects right here. For the people who listen online. If you have questions, you can put in the comment, and I will ask the speaker for you. But at the moment, well, at the beginning, you mentioned about no-hair theorem.
Yes.
Can you wrap up a little bit? What is it about for people who might not have a background about?
So the no-hair theorem is one of the important theorems in GR. It comes from the observation, no, not observation. It comes from the theoretical side of GR, where people notice that all the black hole solution in GR, they only need just 3 parameters in order to describe, the whole object, the black hole itself. So that that's our mass of the black hole, spin of the black holes, and the electric charge of the black holes. And the no-hair theorem says that other than just these 3 parameters, black hole cannot be associated with any physical parameter rather than these 3, which is quite amazed, because given that the black hole is such a complex object, but you only need at least 3 parameters in order to fully describe the black holes. However, this also leads to another problem, because when you're looking from the point of view of gravitational collapse, it seems like some information seems to miss after the black hole form, after the gravitational collapse, because if you have a star, if you have 2 stars which has the same mass and angular momentum, and they collapse to form a black hole, even when they are the black holes, you cannot distinguish, you cannot tell the difference between these 2 objects, because they have the same mass and angular momentum. Right. And that's caused the problem, because some information that could tell us about which star is which seems to be disappear after information goes through the event horizon. So that's kind of no-hair theorem is one of the things that physicists try to validate or to constrain. And because of the gravitational wave and also the shadows, we have a good opportunity to use these 2 experiments to constrain or to study more on the no-hair theorem.
All right. Okay, I see. All right, interesting. So it's mean. So you mean that actually from the result of the gravitational wave, we can somehow use it to confirm whether actually black hole has no hair, right? Something like
the spirit of this is like we expect that if black hole has some hair,
right,
it should produce a different pattern of the gravitational wave when compared with the hairless black holes.
Yeah.
And we hope that by scanning through all the data that we have in gravitational wave or the black hole shadow as well, we hope to see some deviation from the normal GR. But so far GR is still
still safe somehow.
Still there somehow.
All right. So but it doesn't mean that in the future it might change. Well, this kind of perspective, right? If you
sure. Because
more data, right? Something like that.
The gravitational wave just start to detect. The first gravitational wave event is back in 2015, and now today we have detected like quite a lot of events, like I showed to you before in the graveyard plot. That's the event that we have confirmed so far since 2015.
Okay.
And we expect to see more and more of this. This diagram will become like more populated in the future. So we could see something, and we hope to see something.
Okay. All right. Okay. So well, we expect to get more exciting physics in the future, right?
Yeah.
Okay. So and also you mentioned about fastball. which is
Mhm.
actually, if I understand correctly, it's not a black hole, right? Fast ball is something
Yeah,
else.
yeah. So,
And
mhm,
we haven't found them yet, right?
yeah,
Fast ball is just
it's the theoretical.
theoretical object, right?
Mhm.
Right. Okay. Yeah. And again, we expect to use this kind of gravitational wave pattern or to detect whether they exist or not, right?
Yeah. So the research that I told to you before about first ball. So they found that if the first ball emits some gravitational wave, they found that at the early ring down phase, the
Yeah.
ring down phase of the first ball will be similar to the standard black holes in GR. However, when the ring down phase go into a late time, they
Okay.
found that at the late time the decaying rate of the fast ball will be much slower than the standard black holes. So that's kind of thing that we want to 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 do and to observe. Mm.
All right. Okay. Okay. And well, I still have some more question actually.
Yes.
I'm curious about this kind of um, direction of research. So you did something in the higher dimension,
Yes.
black hole in the higher dimension, right? And then, well, I when I listen to the talk from the people who actually study black hole, they normally start to working the black hole with like the sitter space. So
Yes.
I have a very plain question: why do we need to start from that kind of space first? Why do we not just working with just the standard space? Why do we?
You mean why we add lambda? Why we
Yeah,
add?
yeah, that kind of thing. Um,
Well, I believe that because we kind of believe that nowadays we live in the de-sister phase. I mean, the universe is expanding, and the
okay,
de-sister matrix expanding universe.
okay,
So that's one of the motivation, and also from the mathematical point of view and from the physical from the theoretical physics point of view, adding lambda provide a much richer structure of the black hole itself. That you expect to see some other phenomena that you would not normally see in the asymptotically flat space. Like for example, if you go to ADS, especially a black hole in ADS in high dimensions, there's ton of articles that have been studied about these objects because they have some application in the string theory and ADS CFT. On the other hand, the sister counterpart is also interesting because is very explain our physical universe, even though we go to higher dimension.
all right, okay. That is another issue, right? Higher
Yeah,
dimension.
yeah,
Anyway, well, but you can learn a lot from that. I mean, well,
yes,
in terms of mathematics and then and
yeah, and
also physics.
and the metrics that I just showed to you, actually, it is the true form is much more complicated because in higher dimension you are not limited just with one rotation axis.
All right.
Black hole in high dimension, rotating black hole in high dimension in high dimension can rotate in there are so many rotating axes.
Well, very difficult to imagine how.
Yeah. And also even weirder, you can in each axis they could rotate at different like rate as well.
Oh, right.
Yeah, in
Interesting.
the general form, the Mayer-Perry black hole is very general. I mean, you could have arbitrary axis of rotation, and also you could have arbitrary spin rate of the black hole as well.
I see.
This is much simpler version of the matrix.
All right.
Otherwise, I couldn't analyze and study.
All right. Okay. Well, even you say simpler, but well, for me, it's very complicated anyway.
Yeah, it took me like I think almost 3 months just to understand the metric itself.
I see. Right.
Because I before this project I never done higher dimensional object before. This is my that was my first time on the higher dimensional things.
All right. Okay. Very interesting. Okay. So we get a question from the online. I'm going to read for you. Okay. From quasi-normal mode section, why do we consider only the mode with ingoing and outgoing waves? Can other modes describe the ring round phase of the TW due to black hole mergers?
Right. So because we okay. So just to give you some image. What really happens after the merging is the amplitude of the gravitational wave will decay, and that's because when they produce a single object, that single object will try to oscillate, and then they will try to radiate and exist energy away from the source. And we know that if you let the time goes by, at some point the black holes will enter into a equilibrium state again. So then we expect that the wave should be the amplitude of the gravitational wave should be decay with time. And the reasons that the boundary condition of the quasi-normal mode is like this, because from the ingoing wave from the event horizon size is very simple, because here we consider a classical gravity. So if you consider classical gravity, there should be nothing coming out from the black hole, right? Because of the event horizon. So at the event horizon, it's just one way. You can only get into the black hole, not coming out. However, at the asymptotically far region, you can have the outgoing wave, and also you can also have an ingoing wave as well. However, we know that if we change the boundary condition, if you change the physics that we consider, because when we use the mixed outgoing wave and ingoing wave at the asymptotically far regions, the omega will not be described by a quasi-normal mode. It's not going to be a ring down anymore. So in order to obtain the quasi-normal mode, the boundary condition should. So in principle, you should allow your perturbation to radiate away in both sides. Whether the field will absorbed by the black holes or it escape to infinity, but nothing coming in. Sorry.
Right. All right.
So yeah. So that's my answers. I hope that explained.
Okay. So yes, here on this particular page here on this your omega n here, the imaginary part, it look like the harmonic oscillator, right? Somehow.
Yeah. Yes.
It's very interesting here.
So you can see that even the most fundamental mode, when n is equal to 0, you still have an imaginary part.
Yes.
So you won't get normal mode. You will always get your frequency, your omega will always be decay with 1/2 factors.
Right. Okay. Yeah. Very interesting. Anyway, can you? Well, I think we asked a lot. Well, I asked you a lot of questions in physics, and something that related to your research. Can you say something about your research group at Sinpakorn University? That I heard actually you have a group, right?
Well, I have a group, but I'm the only member of the.
Can you say something about that?
So I
might be interested.
Yeah. So I kind of set up my own research group.
Okay.
Grouped. It's called Strong Gravity Group because my research area and my research interests are in the strong gravity regime. So from my PhD, I kind of focus myself onto just a black hole. But nowadays, since we are in the in the era of the gravitational wave and things like this, so I think it would be interesting to extend my interest to cover to some other compact objects like a neutron star or boson star or things like that. And yeah, and at the moment I have one bachelor student who is doing his senior project with me.
All right, good.
Yeah.
Good. All good.
So yeah, I hope it is gonna be okay. And yeah, and I don't know if any of you that listen to this talk and you are interested in this type of thing, and or just to have a chat or something, just contact me some way somehow.
All right.
Yeah, happy to discuss
Yeah,
everything.
definitely.
Yeah.
Okay. Well, there is another question from the audience. Actually,
Mhm.
I'm going to read for you.
Mhm.
What if the author's spin parameter does not vanish in Meyer-Perry black holes? What is the consequence for the existence of both spin parameter in the quasi?
That will change almost everything because at least you have to reconsider your whole analysis on the black hole structures, because the location of the horizon will change, and also if you want to, for example, if there are two spin parameters, then these plot will become 3Ds. For example, you have like a 3D phase space rather than just 2 dimensions.
I see.
And even and not talking about how you're gonna write down these equations. If I remember correctly, if you increase the number of the spin parameter, you will have not just these 2 equations. You will have I can't remember, but probably you will have at least 3 equations for 2 parameters, if I remember correctly. That's some paper that try to study the quasi-normal mode of the Meyer-Perry black holes with is the Meyer-Perry black holes in the sister with a doubly rotation or something. They will have 2 spin parameters, but they set that 2 parameter to be equal.
I see.
Because in I don't know. I mean, if you gonna let everything to be general as much as possible, then I have no idea how to approach the problems at the moment.
Right. Okay.
Or if in the audience you have an idea, you can tell me, and then maybe we can together.
Yeah, definitely. Well, actually, if the audience have, you can contact the speaker directly by to Facebook chat, I believe.
Yes.
All right. Okay. So, well, I think it's about time. I think we come to the end of the event for this afternoon, and I would like to thank our speaker again, Dr. Supachai Pongletskun, for this wonderful talk. And I would like to thank for the online audience who stay with us. Love this 1 hour here, right? Before you go and we go, please spend your time a bit on the survey form. That actually our staff actually put the link on the Facebook comment, and do that for us, please. And well, see you again for next ETH Colloquium number 6, but not in the next month. We come back in Jan next year,
Right.
because
So I'm the last person this year.
Yeah, because next month we're going to have another kind of online event, which is actually going to announce soon. In the Facebook platform. That we'll stay tuned for that. Anyway, we will come back here for the colloquium again in Jan. And today, thank you everyone again, and bye bye. Thank you very much. Bye.
บ๊ายบายขอบคุณครับ thank you
ครับ